Welcome back. I have a pipe here that is connected to the wall at point O on this YZ plane. The pipe goes from point O till point A along the x-axis, then it goes from point A till point B, and notice that the x direction will not change when you go from point A till point B. And then again, you will go parallel to the x-axis like this. As you can see, due to the forces present here, the pipe is subject to two couple moments. One is due to the forces along the x direction, and the other one due to the forces along the z direction. First of all, if I assume that this D here is 400 millimeters between point A and point B, then what is the resultant couple moment due to these four forces? And then the second question is that if I want the magnitude of the resultant couple moment to be 20 Newton meters, then what value do I need to have for my D from point A to point B? So in the first question, the D is given, and you have to calculate the resultant moment. In the second case, your resultant moment is given, and you have to calculate the D. Now, before we jump into that, let's talk about couple moments in 3D a bit. This is my general coordinate frame. This is my origin O. This is my position vector RA. This is my position vector RB. They are all, by the way, on the Y and Z plane. I have two forces here that are equal in magnitude but opposite in direction. Let's call this point A, and then this point, let it be B. Obviously, that creates a couple moment on the plane on which these two forces lie. But what if I want to calculate a moment about point O due to F and minus F, and then add them together to get a resultant moment? Well, I will have moment O equals RB cross F plus RA cross minus F. I can rewrite it like this. In the parentheses, I will have RB minus RA cross F. However, this difference, it's a displacement vector that goes from point A till point B. Let's call this vector R. So this would be your R. And the magnitude of this R is the distance between these two forces. Therefore, we are dealing with couple moments. When we had our scalar formulation, then our couple moment was m equals F times D. But in the vector formulation, the couple moment is expressed in this form. So that's your MO, the moment about point O. In this case, it's a couple moment because it's the distance between these two forces, the perpendicular distance between them in the vector form, cross and then this force F. And this formulation is also useful in 3 dimensions. Here D is simply the distance, but here R is the displacement vector between these two position vectors. Also, make sure that in this formulation, you take this force here, not the negative force, but this one. Essentially, this displacement vector R, its tip needs to touch the force vector, and then you choose that force vector in this formulation. And with that, try solving this pipe problem by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this pipe problem. Firstly, we assume that D equals 400 millimeters, and we want to calculate the resultant couple moment due to two couple moments that this pipe experiences. Let's first get the couple moment due to the vertical forces plus 35 kN and minus 35 kN. The perpendicular distance between these two forces is from point A until this point C, which is the corner of this right triangle. Don't forget you have 90 degrees here at point C. And so I can construct a displacement vector from A till C. It will be this one here, RAC. It goes in the negative y direction. Since you have 30 degrees between AB and AC, your RAC equals minus D times cosine 30 degrees J. And it will be minus 400 times cosine 30 degrees J. This one here, that's your D. And of course it will be in millimeters. And then I compute the couple moment due to these two forces. My displacement vector touches the positive 35 Newton force with its tip. Therefore, the moment due to the vertical forces is RAC cross and then 0I plus 0J plus 35K. We can construct a 3x3 determinant out of it, and so that will give you I times all this plus 0J plus 0K. And that will give me all this in Newton millimeters or all this in Newton meters. So you can see that the moment vector points in the negative x direction. And it makes sense. If you use your right-hand rule, then you see that due to these two vertical forces, your right-hand thumb will point in the negative x direction. Also note that it was important that you use plus 35K for your moment calculations and not minus 35K. That's because the head of this RAC displacement vector needs to touch the force in this way. Then you can apply this formula, R cross F, for your moment calculations, where you use this F and not this one. Then you get the correct direction for your moment. If you want to use this vector minus F, then your R needs to point in the opposite direction. So let's just call it R2. So if you have this configuration, then you would use R2 cross and minus F. Again, that's because the tip of this displacement vector touches this minus F force. So let's say that you want to use minus 35K newtons. Then you have to define a displacement vector RCA, not RAC, where you go from point A to point C, but RCA, where you go from point C till point A, in this way. In that case, it would be D times cosine 30 degrees times J. Now it points in the positive y direction, so it's 400 times cosine 30 degrees times J millimeters. And then I compute my MV, where I use this displacement vector, cross 0I plus 0J minus 35K. Note that now I'm using this one here. So this is my 3x3 determinant. So I will have I times all this plus 0J plus 0K, and that will give me all this in Newton millimeters or all this in Newton meters. You see, you get the same thing. This one is the same like this one here. If you take this displacement vector, RCA, that touches this vector with its tip, but instead you choose this vector, so instead of minus 35k, you would have here plus 35k, then you would have plus here, also plus here, and plus here. But that would be wrong. According to this, your moment is in the positive x direction. But if you apply your right hand rule and you curl your right hand fingers in the rotation direction that these two forces cause, then your right hand thumb will point in the negative x direction. And so if you do something like this, then while you get the same magnitude for your moment, your direction will be wrong. It will be opposite. So be careful with that. Always choose the force that is touched by the displacement vector with its tip. Welcome back. Let's now compute the couple moment due to 50 times I newtons and minus 50 times I newtons. I will construct a displacement vector from A to B along the pipe. So RAB equals 0I minus 400 times cosine 30 degrees times J, which is essentially your RAC, and then plus 400 times sine 30 degrees times K. So this one here, it would be this one here. And then this one, that's RAC. It has no component in the x direction, and so RAB, it's this one here. Since the displacement vector RAB touches the line of action of this minus 50 times I Newton force with its tip, I have to use minus 50 times I Newtons in my moment calculation, and not 50 times I Newtons. And so I get that couple moment like that. I'll write mh, the couple moment due to these horizontal forces in the x direction and minus x direction, it equals RAB cross minus 50 times I. This would be the 3 by 3 determinant. You would have I times 0 minus j times all this plus k times and then all that. And so all that equals all this in Newton millimeters or all this in Newton meters. And there you go. We have our two couple moments in the I, j, and k form. And just like you could add force vectors together and get the resultant force vector Fr, you can do the same thing with moment vectors. You add them up and you get the resultant moment vector. And just like the body would behave in the same way, whether you would apply F1 and F2 to it, or equivalently you would apply Fr to it, in the same way you have it with moments. Either I apply M1 and M2 to a body, or I apply Mr to it. For the body, it makes no difference. But that's only true because we have a rigid body assumption. If bodies deform a lot, and you are unable to make that rigid body assumption, then that's a different story. However, in statics and dynamics, the objects that we consider deform so little that the rigid body assumption is reasonable. And so, the resultant moment for the pipe is the following. Mr equals Mv plus Mh. It's this one plus this one. And so you will get this final answer, or if you want, you can express it in this form as well. So that's your resultant moment when your d equals 400 millimeters. Welcome back. And now the second question was, what d from point A to point B you need to have in order to have a resultant couple moment of 20 Newton meters? Well, here's the thing. Since the directions of RAC and RAB stay the same, meaning that you still have 30 degrees between the AB and AC lines, and all the forces also have the same directions, you know that this resultant moment will also have the same direction. A different magnitude, but the same direction. So this MR here and this MR here, they will point in the same direction. You also know that the magnitude of MR equals MRX squared plus MRY squared plus MRZ squared, and then you square root it, and then you get 20 Newton meters or 20,000 Newton millimeters. You know that because of this information here. So again, MV equals RAC cross, and then this is the positive 35 times K Newton vector that points in the positive Z direction. Now remember that RAC equals 0I minus D times cosine 30 degrees times J plus 0K meters. And so when you calculate all that, then this will be your MV. And notice that now this D is an unknown variable here. Then MH equals RAB cross, and then this force here, that's this one here. Now remember that RAB was 0I minus D times cosine 30 degrees times J plus D times sine 30 degrees times K, again in meters. And so when you evaluate this cross product, then you will get this result. As you can see, you have a D here, and they are your unknown variables. And so all that means is that MR vector equals MV vector plus MH vector, and this is what it all looks like. And then what you will do, you will calculate the magnitude of MR, you will square all the three components of the resultant moment, then you square root it all, and you know that it all equals to 20,000. And that's of course in Newton millimeters, which means that the D will also be in millimeters. And now you have an equation where you have one unknown, which is D. So first of all, I want to get rid of this square root sign, so I have to put here 2, and then I will do the same thing here. And to be formally correct, I should also do it here. Then this square root sign will disappear, and in each term, I will have D squared here, D squared here, and D squared here, which means that I can factor out D squared, and then the rest will stay in the brackets, and all that equals 20,000 squared. Then all this, it will be 13675 over 4. In other words, 3418.75. That means that D squared equals 20,000 squared over, and then all that you had here in the brackets. And then to get rid of this 2 here, over here you're going to put 1/2, and that's 342 millimeters. And there you go. In order to have a magnitude for a resultant moment, which is 20 Newton meters, D must equal 342 millimeters. Thank you very much.